tonight, we're going to break your sense of what a day even is. Imagine you're standing at the south pole of Uranus. You look up and the sun is just hanging there in the sky, not rising, not setting, just frozen at a weird angle for year after year after year. 42 years of daylight. Then without a sunset, without an evening, the lights go out. And you plunge into 42 years of unbroken night. On Earth, your body knows what a day feels like. Morning light, midday glare, sunset, darkness. You know the one. You also know what a year feels like. Spring, summer, fall, winter, looping over and over. Because here's what nobody tells you. Your entire sense of normal seasons is based on a planet that is, by cosmic standards, extremely boring. Now picture Uranus. This ice giant takes about 84 Earth years to go once around the sun. So each Uranian season lasts roughly 21 years. 21 years of spring, 21 of summer, 21 of autumn, 21 of winter. But those words stop meaning what you think they mean when the planet is essentially rolling along its orbit on its side. Uranus's spin axis is tilted by about 98 degrees relative to its orbital plane. So, let's start at the very beginning of the weirdness. Earth is tilted 23.5 degrees, which just gently rocks its hemispheres toward and away from the sun. Uranus is past 90 degrees. It's not just leaning, it's toppled. The result is a world where the poles take turns pointing almost directly at the sun, and then directly away, for decades at a time. So what does day even mean on a planet like that? Technically, Uranus spins once every 17 hours or so. The planet is rotating quickly under your feet. But if you're near the pole during solstice, the sun doesn't care. It just hovers in the same part of the sky while the world spins, because the axis is aimed almost straight at the sun. You get the spin without the sunrise, the rotation without the rhythm. Here's the paradox. Uranus's orbit around the sun is actually pretty normal. It's a slightly stretched out ellipse, not wildly tilted, not plunging up and down through the solar system like some renegade comet. If you only looked at its path through space, you'd expect its seasons to be boring too. So how can a planet that orbits almost like the others end up with seasons that feel like a cosmic prank? How do you get 42-year days from a perfectly respectable orbit? Now let's begin to pull that apart, because once we dig into why Uranus's seasons are more broken than its orbit, we'll have to rethink what season even means, how fragile Earth's kind of normal really is, and what happens when gravity takes a planet and just tips the whole picture sideways. So let's start at the very beginning of what feels wrong here. On Earth, you've been trained to think seasons means a polite wobble, a 23.5 degree tilt, a gentle lean that gives you summer, winter, and a reason to complain about the weather. On Uranus, that picture falls apart. Because this is a world that didn't just lean, it essentially fell over. Uranus's axis isn't tilted a little off the orbital plane. It's tilted about 98 degrees. That means if you drew its orbit as a flat ring and then stuck a skewer through the planet to mark its spin, that skewer would lie almost in the plane of the orbit instead of sticking up out of it. Uranus isn't spinning like a top the way you're used to. It's rolling around the sun on its side. Because here's what nobody tells you. Once you tip a planet that far, the word season stops meaning what you think it means. On Earth, the poles get long days and long nights, sure, but the sun still rises and sets over the year. On Uranus, during a solstice, one pole points almost straight at the sun. For that hemisphere, the sun just hangs there in the sky. No sunrise, no sunset, for about 42 years. Imagine being at the North Pole of Uranus when that happens. The sun circles lazily overhead for decades, never dipping below the horizon. You live, age, and die in one unbroken, washed-out afternoon. On the other side of the planet, 42 years of unending night. No dawn, just a dim turquoise glow from the upper atmosphere and the distant whisper of the solar system beyond. Each Uranian year is about 84 Earth years, so each season lasts roughly 21. A single summer or winter there is longer than many human lives. If our modest tilt can carve out ice ages, shape agriculture, and decide where whole civilizations rise, what does almost half a century of daylight or darkness do to a climate? What does it do to any hypothetical life trying to adapt to a sky that forgets how to turn off the lights? And yet something is above the planets. Something is below them, because Uranus doesn't just break your mental picture with its tilt. It breaks it again with a magnetic field that refuses to line up. The magnetic axis is tilted about 59 degrees from the spin axis and shoved off-center by roughly a third of the planet's radius. So the seasons of sunlight, the seasons of rotation, and the seasons of magnetism are all out of sync, all tugging on the atmosphere in different rhythms. Now let's begin to see why that matters. When Voyager 2 flew past near southern summer, Uranus looked quiet, almost boring, as if the long daylight had flattened its weather. Later, as the planet moved toward the equinox and the sun hit the equator instead of the pole, telescopes on Earth started catching storms popping up out of nowhere. Calm for decades, then suddenly boiling. So what kind of world lives under seasons like that? A planet where winter means darkness for generations, where summer can hide storms until the geometry of light and magnetism lines up just wrong. In the next part, we're going to dive into how a sideways spin, a lopsided magnetic field, and a strangely moody atmosphere all lock together, and what that reveals about how fragile our own version of normal really is. And if your brain is already buzzing from that, you're not alone. If the idea of a planet rolling around the sun on its side, serving up 42-year days and 42-year nights, has you quietly renegotiating what a normal planet even is, you are exactly the kind of person we made this for. Because here's what nobody tells you. Once one world breaks your mental model, you start seeing cracks in the whole solar system picture. So if you like that feeling, that moment where you go, wait, we can do that? This is where we ask you to do the easiest possible thing that actually matters. Tap like, hit subscribe. That's it. 2 tiny clicks in your orbit. Big gravitational pull on ours. Here's why it matters more than it should. Missions follow money. Money follows attention, and Uranus does not get attention. It has one flyby from Voyager 2, a handful of Hubble and ground-based images, and then it's back to glamorous worlds like Mars and Jupiter. When you interact with a video about a quiet ice giant, you're telling the algorithm, and eventually the people who fund missions, that weird, underloved planets are worth pointing cameras at. We get to spend weeks buried in data, weird papers, and old Voyager images, because those clicks buy us time. Time to chase the planets that don't have rovers, landers, or glossy tourism posters. If you want more deep dives into broken worlds, strange physics, and the parts of space that textbooks sprint past, this is how you vote for that. Now let's make this an actual conversation, not just a lecture from a floating voice in your headphones. Imagine you had to live on Uranus, not on the clouds, not in the core, just pick your latitude. Would you choose the equator, where you get something closer to a regular day-night cycle, Slow, cold, but at least the sun rises and sets? Or do you go full chaos and move to a pole where the sun parks in the sky for decades, then vanishes for just as long? Drop your answer in the comments, equator or pole, and tell us why. You know, the one that secretly tempts you, the one that fits how your brain wants to experience time. Because once you try to imagine actually living through those seasons, you realize how fragile our own definition of normal really is. And yet, something is above the planets. Something is below them. Before we can judge Uranus for being weird, we need to ask a more uncomfortable question. What would a truly normal planet even look like? So, let's start at the very beginning. What are seasons supposed to be, and when did our idea of normal quietly break? So let's start at the very beginning with the version of the solar system that lives in your head right now. You know the one. The neat classroom poster with the sun in the middle, glowing like a perfect yellow target, and all the planets lined up on those thin, clean tracks, like grooves on a record. In that picture, the solar system is flat. Every orbit is a circle drawn on a single sheet of paper. Mercury, then Venus, then Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all laid out in order like colored coins on a table. No one is floating above or below anything. They're all pinned to the same invisible tabletop, the same plane. Astronomers give that tabletop a name, the ecliptic plane, defined by Earth's orbit around the sun. In the textbook version, all the planets politely follow it. They glide along those flat tracks with almost clockwork precision, as if gravity were a patient teacher keeping every marble in its lane. The message is quiet but powerful. This is how a solar system is supposed to look: orderly, flat, predictable. Now let's begin on seasons in that same tidy world. You're told Earth is just a slightly tilted spinning globe, leaning at about 23.5 degrees. Not sideways, not dramatic, just a modest nod. As we orbit the sun, that tilt means the northern hemisphere leans toward the sun for part of the year, and away from it, 6 months later, trading places with the southern hemisphere. Because here's what nobody tells you. That little tilt is doing almost all the work. When your half of Earth leans toward the sun, sunlight hits you more directly. The days stretch longer, and you call it summer. When your half leans away, the light comes in at a shallower angle. Days shrink, and you call it winter. Same orbit, same distance, just geometry on a flat plane. The way it's drawn, Earth looks like a marble rolling around a circular track on a tabletop, spinning more or less upright as it goes. Mars is another marble. Venus is another. All of them sitting on that same flat surface, all with small, tasteful tilts that give them gentle, familiar seasons. No one is doing cartwheels. No one is rolling on their side. So your brain quietly absorbs a rule. Planets orbit in one flat plane. They spin almost straight up. And seasons are just mild variations on that theme. Orbits are tidy. Tilts are modest. Seasons are well behaved. And yet, something is above the planets. Something is below them. The real solar system cheats on almost every one of those rules. And Uranus doesn't just cheat. It breaks the answer key. To see how far it goes, we have to take that flat picture and start bending it until it almost snaps. So let's talk about that picture you grew up with. You know the one. The solar system laid out like a tidy clock, perfect circles, planets politely spaced, all standing almost upright as they glide around the sun in a razor-thin, flat plane. That picture isn't a lie, but it is a magic trick. It's drawn from one very specific vantage point, and then it quietly convinces you that this is the only way to see the solar system. Because here's what nobody tells you. A two-dimensional diagram has to crush an untidy, three-dimensional reality into something your notebook can handle. And in the process, it hides almost all the chaos that made those orbits possible in the first place. Look at those little tilt angles in the diagram. Earth leaning at 23 degrees, Mars at 25, Saturn tipped a bit more. They're all drawn as small, tasteful slants. So your brain does something sneaky. It decides that real planets are mostly upright, that a gentle tilt is normal, and that anything more dramatic must be rare, unstable, or practically impossible. If every poster in your classroom shows planets politely nodding, never imagine one doing a full cartwheel. Now let's begin to peel that picture off the page. Imagine flying a spaceship straight up out of the solar system, away from the ecliptic plane the diagram worships. Very quickly, those neat rings of orbit shrink into a thin, glowing disk of motion, cutting across a huge, mostly empty volume of space. The vertical thickness is there, but compared to the width, it's a hairline. From above, the orbits look aligned. From the side, you finally see how fragile that alignment really is. Because the hidden assumption in that flat picture is brutal. It pretends that orbits and tilts want to be tidy, that planets naturally agree on a plane, that a solar system is born as a clockwork and only gets disturbed later. But the truth is the opposite. The collapsing cloud that formed our solar system tried to throw material everywhere. And only gravity plus billions of years of collisions, mergers, and near misses hammered it into something that looks orderly from one lucky angle. So when you see Uranus drawn on that same polite diagram, just another circle on the same flat track, your intuition screams that its 98-degree tilt is a glitch. It looks like a typo in the cosmos. In reality, it's a clue. A sideways planet with broken seasons isn't the exception to some universal rule of neatness. It's a fossil scar from how violent planet building really was. And yet something is above the planets. Something is below them. Once you follow Uranus out of the diagram and into three-dimensional space, you start to see what those scars actually do to a year, to a day, and to the light from the sun itself. Because if a planet can roll around the sun on its side and still keep its orbit, what does that do to sunrise, sunset, and the very idea of a season? To answer that, we have to land on Uranus and watch an entire hemisphere vanish into night. But we can do something even stranger. We can leave. So imagine we climb back into our mental spaceship, fire the engines, and punch straight up out of the solar system from Uranus's position, not along the orbit, not toward the sun, straight off the diagram. Now let's begin to break that flat picture your brain has been clinging to. As we rise, Uranus shrinks into a tiny blue-green bead below us. The rings turn into a faint, tilted halo. The sun and the other planets start to slide together in your window, compressing into a bright, thin line in one direction. You know the one. That textbook side view where everything suddenly looks like a razor-thin disk. From up here, the whole solar system looks astonishingly orderly, because here's what nobody tells you. From above, Uranus's orbit looks almost boring. It's nearly circular. It lies close to the same orbital plane as Jupiter, Saturn, Neptune, Earth. No wild tilt, no comet-like eccentricity, no dramatic plunge above or below the plane. If you just trace the path of the planet around the sun, you'd say, "Yep, another well-behaved member of the family." The orbit is not what's broken. Now we zoom back in. We swing our view so we're looking edge-on at that orbital plane, the way you'd stare along the surface of a glass table. Most planets would look like spinning tops gliding around the edge. Uranus does not. Uranus's spin axis is almost lying in that plane, tipped about 98 degrees, like someone knocked a globe off its stand and it kept rolling. It's not a top, it's a rolling ball. Here's the paradox. From the outside, the track is normal. From the inside, the ride is not. If you were standing near Uranus's pole, your up would be almost directly along its orbit, not away from the sun. For decades at a time, that pole can stare almost straight into sunlight, while the opposite pole is locked in unbroken night. 42 years of day, 42 years of darkness. On a planet whose year lasts 84 Earth years, your whole life could be one long sunrise that never quite ends. And yet something is above the planets. Something is below them. From this vantage point, you see that above and below the plane of the orbit are not the same as above and below on the planet itself. Our flat diagram quietly welded those ideas together. Uranus rips them apart. So if the orbit isn't the problem, what twisted the planet's own orientation so badly that its seasons shattered, while the path it follows stayed so neat? What kind of event can leave the track intact, but send the spinning world on it tumbling sideways? So that's the puzzle on the table. The track is tidy, the marble is wrecked. Now we have to ask a bigger question. Is Uranus the oddball of the solar system? Or is our idea of a normal planet just too flat, too Earth-centric, too polite for what gravity actually does in space? Because here's what nobody tells you. When we call Uranus weird, we're really revealing our own bias. You grew up with that picture of planets as upright spinning tops on a shared, almost perfect plane. You know the one. Neat circles, gentle tilts, everything behaving. But Uranus doesn't just lean a bit. With a tilt of about 98 degrees, it's effectively rolling around the sun on its side, and that forces us to ask, are we looking at a freak accident, or a preview of how planets usually end up when you let them smash around in a young planetary system for a few 100 million years? So, let's start at the very beginning of what we actually want to know here. We're going to split this into 3 layers. First, what do Uranus's seasons actually feel like on the ground? Or at least, in the clouds? What happens to summer and winter when one pole can stare at the sun for 42 years straight, while the other is locked in decades of darkness? Second, how does a world get knocked so far over that its equator points almost where we'd expect a pole to be? And third, what do its broken seasons and its lopsided magnetic field tell us about how planets form, evolve, and tear up our tidy diagrams? To do that, we need to separate 2 ideas your brain quietly welded together: orbit and spin. Uranus's orbit around the sun is mostly fine. It's not wildly tilted compared to the other planets. It's not plunging above and below the solar system's main plane like some rogue comet. The path is boring. It's the rotation that's deranged. The way the planet spins, the way its interior sloshes, and its magnetic field sprouts out at a crazy angle. Those are where the real fractures show up. And yet something is above the planets. Something is below them. Not in the diagram, but in 3-dimensional reality, where collisions, migrations, and tilted magnetic fields are the rule, not the exception. By the end of this, we want that childhood image of upright marbles on a flat track to feel incomplete. Still useful as a map, but obviously a lie of omission. Because once you see Uranus clearly, you start to suspect it's not alone. Out in the galaxy, there could be countless sideways ice giants orbiting other stars, with seasons and magnetospheres that make ours look tame. So next, let's dive into what a year on a sideways world actually looks like, and why its sunrise and sunset schedule should make you rethink what a normal planet even is. To really understand how Uranus ended up rolling around the sun on its side, we have to do something drastic. We have to delete it. Not just Uranus, but every planet, every moon, every neat orbit in that flat textbook diagram. You know the one. Now let's begin by rolling the clock back 4.5 billion years. The solar system doesn't exist yet. There is no ecliptic plane, no up or down, no broken seasons. There's just a cold, dark region of space filled with a giant, invisible character in our story, a molecular cloud. Picture it stretching for light years. It's not a tidy ball. It's a ragged, lumpy cloud of gas and dust, mostly hydrogen and helium, with a tiny sprinkling of heavier elements. Those heavier bits, iron, oxygen, carbon, silicon, were forged in earlier stars and blown out by supernovae, then mixed into this region over millions of years. Because here's what nobody tells you. Uranus's weirdness starts long before there's a planet. It starts in that enriched, uneven cloud. Inside this cloud, atoms drift in slow, random motions. Left alone, it would just sit there, but gravity doesn't leave things alone. Over time, slightly denser patches pull a little harder. They attract more material, get denser, and pull harder still. The whole cloud begins to collapse inward, and as it does, all those random motions average out into a net spin. Not because the universe likes order, but because tiny imbalances add up when you're dealing with something this vast. As the collapse speeds up, that spin matters. The cloud can fall inward along the spin axis, but material trying to move across the equator gets flung outward by angular momentum. The result is a transformation from a puffy three-dimensional cloud to a flattened, rotating disk around a growing protostar that will become our sun. So let's start at the very beginning of flat here. This is the first real plane of our solar system's history. Most of the material sinks into that disk. Pebbles become boulders. Boulders become mountain-sized worlds. And those worlds crash, merge, and scatter each other as they orbit. In that chaos, some spin fast, some slow, some get tilted by glancing blows, others get nearly flipped by catastrophic impacts. And yet, something is above the planets, something is below them. At this stage, nothing guarantees that any future planet will end up politely upright. Tilts, spins, and even orbits are negotiable, written by collisions and close passes. Which means Uranus's sideways lean isn't a violation of the rules of formation. It is the rule, taken to an extreme we're about to explore. So if tilts and orbits are negotiable, we have to ask a deeper question. Negotiable out of what? What raw material did Uranus and its siblings start with before the violence began to rewrite them? Now let's begin with something almost insultingly small. Dust. Tiny grains floating in the young solar system's protoplanetary disk, orbited in a broad, flat plane around the infant sun. At first, they just drift, but collisions at walking speed let them stick together. Electrostatic forces gluing grains into pebbles, pebbles into rocks, rocks into boulders. You know the one. The classic slow motion's snowball effect, but happening in space. Because here's what nobody tells you when you see that neat textbook picture of planets already in place. Long before there were worlds, there was a traffic jam of growing clumps. As they bulked up, their own gravity kicked in, helping them sweep up more material. Once you reach kilometer-scale planetesimals, the game changes. These are no longer dust motes. They're baby worlds, each one on its own slightly different orbit, each one capable of smashing, merging, or shattering. Closer to the sun, only metals and rock can survive the heat, so you get the ingredients for Earth-like planets. But move outward, beyond a certain distance, and the chemistry of the disk flips. Cross the so-called frost line, and water, ammonia, and methane can freeze into solid ice grains. That's crucial. It means that in the region where Uranus and Neptune will one day orbit, there's far more solid material available than in the inner solar system. So, let's start at the very beginning of the ice giants themselves. Out there, icy planetesimals collide and merge into frigid cores several times the mass of Earth. Each new impact adds not just rock, but frozen water and other ices, building dense, icy super-Earths. Their gravity becomes strong enough to tug in the surrounding gas, and yet more ice from the disk, puffing them up into worlds that are too big to be rocky, too small to be Jupiters. We call them ice giants, but they're really layered hybrids. Rock and ice in the middle, wrapped in envelopes of hydrogen and helium. During this growth spurt, the disk is anything but peaceful. Orbits cross. Protoplanets migrate. Some get kicked inward, some flung outward, some erased entirely. Collisions between Mars or even Earth-sized bodies are not rare catastrophes. They're the main way planets finish forming. A single glancing impact can tilt a spin axis, strip an atmosphere, or leave a world spinning backwards compared to its orbit. And yet, something is above the planets. Something is below them. In this three-dimensional shooting gallery, upright is an accident, not a guarantee. Somewhere in that violent cloud of icy building blocks, one impact on the growing Uranus wasn't just a nudge. It was a cosmic body check that may have rolled the entire planet onto its side. But what does that actually do to a year, to daylight, to seasons on a world that orbits like a rolling ball? That's where Uranus stops being just weird and starts to feel almost impossible. On a sideways world, seasons break. But here's the twist. Uranus's broken seasons only make sense when you see how surprisingly well behaved the rest of the solar system is. So, let's start at the very beginning. Picture that original collapsing cloud of gas and dust, the one that spun itself into a flat disk around the newborn sun. In a disk like that, gravity and collisions are ruthless editors. Anything on a wild, tilted path keeps plowing through the disk, hitting other objects, getting tugged, slowed, shaved down. Over millions of years, those random inclinations get damped out, and the orbits settle into the same thin plane. Because here's what nobody tells you. The disk doesn't just feed the planets. It trains them. It encourages them to move together, to orbit in the same direction, in almost the same flat sheet of space. That's why, when you line up the major planets, you get this elegant, nearly level family portrait. Their orbital planes are all close to Earth's orbital plane, the ecliptic, like grooves on the same record. You know the one? Mercury's orbit is tilted a bit, Mars a little, Neptune a little more, but they're all still playing by the same rules. The result is that the solar system really does look like a flat disk from a distance, with just a bit of thickness. And yet, something is above the planets. Something is below them. Asteroids, comets, tilted debris. But the 8 big planets, they're the disciplined ones. Their spins tell the same story. Earth leans at about 23.5 degrees, giving you familiar seasons without flipping the world upside down. Mars is close, around 25 degrees, so its seasons feel like an exaggerated Earth. Jupiter barely tilts at all, just about 3 degrees, a giant almost standing upright in the planetary plane. Saturn lounges a bit more at 26 degrees, but still, its poles never lie flat along its orbit. So by the time you've met those 4, your brain has a pattern. Small tilt, moderate tilt, gentle seasons, nothing too wild. Then you hit Uranus, and the pattern snaps. Uranus doesn't just lean. Its axis is tilted nearly 98 degrees, past horizontal. Its spin axis is almost lying in the same plane as its orbit. So as it circles the sun, it's not spinning like a top, it's rolling like a ball. One pole spends decades staring almost directly at the sun, while the other stares into deep space. Here's the puzzle that should bother you. If the original disk worked so hard to iron out chaos, what could possibly be violent enough to override all that training and leave Uranus rolling on its side? Something hit it, or torqued it, so hard that the neat, flat picture of the solar system has this one glaring exception. And once you see that, you have to ask, what does that do to a year, to daylight, to weather, on a world that broke the rules that shape every other planet we know? So if Uranus broke the rules, the next question is brutal and simple. Who hit it? Now let's begin with the version most planetary scientists quietly bet on. Picture the early solar system not as a calm, flat diagram, but as a crowded construction zone. Protoplanets the size of Mars, Earth, even bigger, are sharing orbits, crossing paths, and occasionally playing cosmic bumper cars. Because here's what nobody tells you. The finished solar system you see in textbooks is the peaceful end state of a long, violent brawl. In that chaos, Uranus is thought to have taken a glancing blow from one of those giants. Not a head-on smash that would rip it apart or eject it from its orbit around the sun, but a sidelong collision. You know the one, when you spin a toy top and then flick it hard from the side, so it starts wobbling in a new direction without actually flying off the table. The impactor plows through Uranus's outer layers, dumps a huge amount of angular momentum into the planet, and then either merges or gets shredded into a cloud of debris. That's the heart of the great cosmic hit-and-run theory. A single, well-timed giant impact can torque a world. Gravity keeps Uranus bound to the sun, so its path through space, its orbital plane, stays mostly the same. But its spin axis, that's negotiable. Tilt it by a few tens of degrees. Tilt it by 98. The orbit doesn't care as long as the total energy budget still works out. When teams run computer simulations of these early impacts, something eerie happens. If they slam Uranus with one Earth mass body at a shallow angle, or with a series of slightly smaller protoplanets, they can reproduce not just the wild axial tilt, but also a ring system and a family of moons that end up orbiting in that same bizarre orientation. Rings can form from the shattered remains of the impactor. Moons can condense out of that flattened debris cloud, locked into the new equatorial plane of a sideways planet. And inside, that hit wouldn't just tilt the outside and walk away. It could have churned Uranus's interior into layers, or created a slushy, partially mixed mantle that still controls how heat leaks out. It might even explain why the magnetic field is so misaligned and offset, as if the dynamo is running in a lopsided shell rather than a neat, central core. In other words, the collision didn't just rotate the planet, it rewired it. Which leaves us with a strange thought. If one ancient impact can rewrite a planet's tilt, its rings, its moons, its magnetic field, what did it do to time itself on Uranus? What does a year feel like on a world where a single collision permanently broke the link between day, season, and sunlight? So what does that broken link actually look like day to day on a world that got knocked sideways? To feel it, you need to stop thinking of a planet spinning like a top and start picturing a planet that rolls. Now let's begin with something you can hold in your hands. Grab a basketball. That's Uranus. Grab a flashlight. That's the sun. In your usual solar system picture, you'd spin the ball with its poles pointing up and down, then walk it in a circle around the light. Simple. The ball spins like Earth. The beam hits the equator most directly, and the poles just skim the edge of the glow. But Uranus refuses to play that game, because here's what nobody tells you. To get Uranus right, you have to tip the basketball almost all the way onto its side, so that one pole is nearly pointing at the flashlight. Now walk it around the light like that. You're not spinning a globe on a stand anymore. You're rolling a ball around the room. And yet something is above the planets. Something is below them. On Uranus, that above-below isn't north and south the way your brain expects. It's more like forward and backward along its orbit, because the axis is lying almost in the orbital plane instead of poking out of it. Here's the wild twist. Uranus still rotates fast. A Uranian day is only about 17 hours. So if you were standing near the equator, the sky would still whip overhead, sunrise to sunset, in less than an Earth day. But because the whole planet is tipped over, those 17-hour spins line up with sunlight in a completely different way as it crawls through its 84-year orbit. At solstice, that sideways geometry goes to the extreme. One pole leans almost directly into the sun, soaking in continuous daylight, spin after spin, for about 42 Earth years. The opposite pole, locked in a night that also lasts decades. The planet keeps rotating, but near the pole, the sun just sits there, fixed in the sky, or never appears at all. Contrast that with Earth. At our poles, the sun does weird loops, circling the horizon, but over the course of a year, you still get a sunrise season, a sunset season, a kind of rhythm. On Uranus, that rhythm is stretched and distorted. What Earth does in months, Uranus drags out over generations. Imagine being born in the light and not seeing a true night until middle age. So, let's start at the very beginning of the mystery. There's nothing especially broken about Uranus's orbit. It goes around the sun in a pretty normal ellipse. What's catastrophically misaligned is the spin axis itself. That sideways orientation is the root cause of its shattered seasons. The reason day, year, and sunlight no longer agree. But if a planet is rolling instead of spinning, what happens to its weather, its rings, even its magnetic bubble in space when one hemisphere bakes for decades and the other freezes in shadow? So let's zoom out and put numbers on this broken symmetry. Uranus takes about 84 Earth years to complete a single orbit around the sun. 1 year. 84 of our years. Because here's what nobody tells you. When you tilt a planet almost onto its side, that 84-year loop doesn't just give you a long year, it stretches the very idea of season, until it barely resembles what you experience on Earth. Divide that orbit into 4 seasons and you get the first unsettling result. Roughly 21 Earth years per season. 21 years of spring. 21 years of summer. Then autumn. Then winter. So, let's start at the very beginning of that cycle. Picture Uranus at a solstice. One pole is tipped almost directly at the sun, soaking up continuous daylight, while the opposite pole is locked in unbroken night. Half the planet is in an endless day mode, the other half in an endless night mode. And the boundary between them is where the weirdness really lives. Now, as Uranus crawls along its orbit, gravity keeps it in that sideways orientation, but the direction of that tilt relative to the Sun slowly shifts. Over about 21 years, the planet glides from solstice toward equinox. At equinox, the equator is what faces the Sun, and the poles finally get a kind of relief. The Sun rises and sets there for the first time in decades. Then Uranus keeps going, and 21 years later, it reaches the opposite solstice, with the other pole now staring straight into the light. On Earth, the Sun's path in the sky climbs and dips over a few months. You feel that as quick, familiar seasons. On Uranus, the same change is stretched across decades. At a pole, the Sun doesn't gently arc from horizon to overhead in a single day. It inches its way up over years. Imagine watching the Sun hug the horizon for most of your childhood, then very slowly, year after year, creep higher until it finally circles overhead without ever setting. And then, it reverses just as slowly, taking another 20+ years to slide back down and vanish. Mid-latitudes don't escape. They still get something like spring and fall, but the transitions are glacially slow. Temperature, winds, and light levels don't swing with a quick annual rhythm. They drift. You could spend 5 years in what feels like a drawn-out late afternoon. And yet, something is above the planets. Something is below them. In this flat mental picture of seasons, Uranus quietly refuses to fit. Now hold the strangest thought experiment in your head. If you were born at the start of a polar summer on Uranus, you might live your entire life under a sun that never sets, watching it slowly circle the sky, dying of old age before true night ever returns. What does weather even mean on a world where a sunset can be a once-in-a-century event? On Uranus, that thought experiment isn't a cute exaggeration. It's the weather report. Now let's begin at the pole itself. Pick the North Pole, for example. Freeze the solar system in your mind at Uranus's summer solstice, when that pole is tipped almost directly at the Sun. The Sun doesn't rise. It doesn't set. It just hangs there, high in the sky, slowly circling like the hand of a clock that's forgotten how to tick, blazing down for about 42 straight Earth years. Not 42 hours, not 42 days. 42 years of unbroken daylight on a world already sitting 4 times farther from the Sun than Earth. Because here's what nobody tells you. Even at that distance, if you never give a planet's atmosphere a chance to cool, the energy adds up. Day after day, year after year, the same hemisphere is marinated in low, cold sunlight that never truly turns off. Now slide your mental camera to the other end of the axis. The South Pole, at that same moment, isn't just having a long winter. It's erased from the Sun's point of view. For those same 42 years, the Sun never climbs above its horizon at all. The sky there is a permanent midnight dome, broken only by faint starlight and the thin, ghostly glow of Uranus's rings sweeping overhead like a tilted halo. Every so often, an aurora might ripple across that darkness, powered by a magnetic field that's already misaligned and off-center. You know the one. Tilted almost 60 degrees from the spin axis and shoved away from the planet's core, so its curtains of light don't politely crown the pole the way Earth's do. They twist and wander, throwing brief, eerie weather into a night that otherwise lasts longer than many human lives. On Earth, polar day and polar night last a few months. Long enough to be disorienting, but still something you can put on a calendar. On Uranus, those words stop sounding like seasons and start sounding like ages. A summer you're born into and never live to see end. A winter your grandparents vanished into, with stories about the last sunrise that feel more like mythology than meteorology. And yet something is above the planets. Something is below them. It's the same sun, the same gravity, the same orbital mechanics, but stretched to a time scale where climate has to think in decades just to blink. One hemisphere is slowly baked, the other is slowly frozen. Heat seeps down into the deep atmosphere and interior, fighting that darkness with glacial patience, while the cold hemisphere hoards its chill, refusing to warm quickly when its turn in the light finally comes. So what does an atmosphere do under that kind of schedule? What would clouds, winds, or any hypothetical ecosystem look like when spring is a 20-year transition and night can span your entire biography? As Uranus rolls along its orbit, we're left with a bigger question. How do you build stability on a world where even sunrise and sunset are once-in-a-lifetime events? On Uranus, there is one moment in the year when that once-in-a-lifetime sunrise stops being rare. It becomes global. It sweeps across the whole planet in slow motion. That moment is equinox. Not just the polite, blink and you miss it, equinox you're used to on Earth. This is Uranus turning its equator toward the sun, hauling itself out of its sideways pose so that, for a while, day and night are shared more evenly across latitudes. Because here's what nobody tells you. On a world that spends decades with a pole staring straight into the sun, evenly is already a revolution. So what does that actually look like from the outside? Picture Uranus rolling along its 84-year orbit. For about 21 years at a time, one hemisphere has been basking in a sun that never really sets, while the other has been locked in a deep, unbroken night. At equinox, that frozen, forgotten hemisphere finally rotates into the light. The long sunlit side, overexposed for decades, begins to tilt away and cool. Regions that were in darkness longer than a human career get their first dawn. The places that were overlit start to dim, and the planet reacts hard. You know the one, that textbook image of Uranus as a bland, pale blue cue ball. Voyager 2 saw something close to that in 1986, when it flew past near southern summer solstice, and most of the illuminated pole had been calmly sunlit for ages. But as Uranus approached equinox in the 2000s and 2010s, telescopes on Earth and in space started catching a different picture. The planet brightened. High-altitude clouds popped into view. Storms, actual trackable storms, flared near the equator and mid-latitudes. So what changed? The sunlight pattern. When the equator faces the sun, the energy input stops being a simple on at one pole, off at the other. Switch. It spreads. That shift in where the heat goes can reorganize atmospheric circulation, push winds into new lanes, and trigger cloud formation in regions that were quiet for half a century. It's like taking a planet-sized weather system that's been stuck in one configuration and giving it a shove. Because once you start turning on a hemisphere that's been radiating its heat away in the dark for decades, the temperature contrasts sharpen. Convection ramps up. Methane-rich layers that were stable in the cold begin to rise, condense, and form bright clouds. The rings even change in visibility as the viewing geometry and the way they scatter sunlight shift around equinox, reminding you that nothing in this system is truly still. And yet, something is above the planets. Something is below them. Wrapped around Uranus is a lopsided magnetic field and a deep, layered atmosphere that both feel these seasonal jolts in slow motion. Beneath that soft blue haze, Winds and fields are twisting to a rhythm you can't see from a flat diagram. So what is that hidden weather engine actually doing down there? And how broken can a magnetosphere get before it stops making sense? To answer that, we have to look at the planet that fooled us for decades. Because here's what nobody tells you. When we first saw Uranus up close, it looked like nothing was happening at all. Voyager 2 finally swung past in 1986, the only spacecraft ever to visit, and the images were almost disappointing. You know the one. A nearly featureless, pale blue-green sphere with only the faintest hints of bands if you really squinted. No roaring great red spot like Jupiter. No dramatic rings and storms like Saturn. Just a soft, smooth cue ball hanging in space, looking more like a screensaver than a living world. That quiet color is a clue. Sunlight dives into Uranus's upper atmosphere, and methane gas grabs the red wavelengths, absorbing them and letting blue and green leak back out to your eyes. Beneath that haze sit deeper layers of hydrogen and helium, mixed with ices like water, ammonia, and methane under crushing pressure. So on the surface, it looks simple. Underneath, it's a layered fluid giant with room for all kinds of hidden motion. For a long time, though, the verdict was boring. Compared to the chaos on Jupiter, Uranus showed almost no visible storms, barely any swirling clouds, and a surprisingly low internal heat output. It doesn't radiate much more energy than it gets from the sun. So the picture that stuck was a cold, sluggish planet that just rolls along its orbit, doing as little as possible. Now let's begin to break that picture. As our telescopes sharpened and we watched Uranus crawl through its 84-year orbit, something changed. Near equinox, when the sun crosses its equator and both hemispheres share the light, that dead disk suddenly grew scars and stripes. Subtle cloud bands emerged. Bright storms popped up near the mid-latitudes. Infrared images revealed hot spots and temperature contrasts that Voyager never saw. Pattern interrupt. The most boring ice giant in the solar system turns out to have weather that waits decades to reveal itself. What kind of atmosphere does that? The answer is one that's being driven in slow motion by those broken seasons we talked about. On Uranus, sunlight doesn't just shift a little north and south like it does on Earth. It can linger over a pole for 42 years, then swing toward the equator, then drown the opposite pole in decades of darkness. The atmosphere doesn't respond with quick, flashy hurricanes. It responds with deep, gradual rearrangements of winds and clouds that only become obvious as the geometry of light changes. So, let's start at the very beginning of what this really means. Even a planet that looks flat, calm, and almost featureless can be hiding a complex three-dimensional engine underneath, tuned to a rhythm of seasons longer than a human lifetime. And if the visible clouds are only the faintest hint of that rhythm, what are the deeper layers doing as Uranus tips from solstice to equinox and back again? So let's start at the very beginning of what that engine is actually made of. When you look at Uranus, you see a pale, almost flat-looking disk on the screen. But that calm face is just the thinnest skin of a layered atmosphere. Upper hazes hanging like a photochemical fog, methane clouds forming and dissolving below, and then deeper down, high-pressure layers of hydrogen and helium, pressing on what might be a super-compressed water-ammonia ocean. It's not a solid world. It's a vertical stack of climates. Because here's what nobody tells you. On a sideways planet, those layers don't all feel the seasons in the same way, or on the same schedule. When one hemisphere spends decades tipped towards the sun, The energy first seeps into those upper hazes, molecule by molecule, year by slow year. The deeper layers barely notice at first, but the top starts to warm, the temperature gradients shift, and the wind patterns that were quietly cruising along for decades get nudged off balance. Imagine the North Pole locked in 42 years of day. The sunlight doesn't blast the planet like it would at Mercury. It whispers. For Uranus, that whisper is enough. Tiny changes in heating can relax some jet streams and tighten others, letting vertical motions sneak through where they were once suppressed. Regions that were kept by stable, stratified air can suddenly breathe. The result? Storms that weren't allowed before can finally rise. You see this most clearly when Uranus passes through equinox, when its equator, not its pole, faces the sun. Voyager 2 caught the planet near southern summer solstice, and it looked bland, almost featureless. But as we watched from Earth decades later and Uranus approached equinox, bright storms started popping up. Bands sharpened, and dark regions that had been hidden in shadow for years lit up and changed character. It's as if the moment-long frozen twilight zones taste sunlight again. Latent energy that's been stored in those deep layers gets released in slow motion. Now, compare that to Jupiter. On Jupiter, storms are loud, they're fast, chaotic, filmed in real time. The Great Red Spot is a centuries-long hurricane, but its smaller vortices can spin up and die in days. Uranus is playing a different game. Same physics, different tempo. Its year is 84 Earth years. Its seasons last decades, so the atmospheric circulation respond on a stretched-out clock. A single storm outbreak on Uranus can be the atmospheric equivalent of a slow inhale that takes half a human lifetime. So you have to wonder, if we could watch Uranus in time-lapse over thousands of years, would it look as wild as any gas giant, just running in ultra-slow motion? Would bright clouds flicker across that pale disk like lightning in a dim room, too slow for one generation to notice? And yet, something is above the planets. Something is below them. The next question is how that sideways magnetosphere rides through this drifting seasonal atmosphere. That sideways magnetosphere isn't alone out there. It's plowing through a whole halo of debris. Because Uranus doesn't just have weird seasons on its clouds. It has seasons for dust and ice. Now let's begin with something you almost never see in the usual flat diagram. The rings of Uranus. You know the one, with Saturn hogging all the ring glory. Uranus's rings are the introverts of the solar system. Narrow, dark, and razor-thin, discovered in 1977, not by pretty pictures, but because they briefly blinked out starlight as the planet passed in front of a background star. 11 sharp-edged main rings, made of dust and ice that's so dark it reflects only a few % of the sunlight that hits it, yet still arranged in tight, dynamic bands. Because here's what nobody tells you. On a sideways planet, the rings inherit the weirdness. They're not just circling a ball. They're wrapped around a rolling world, as Uranus orbits the Sun over its 84-year year. The tilt of that ring plane relative to us changes dramatically. Sometimes we see them almost face-on, a delicate, glowing target around the planet. Sometimes the whole system turns so thin that, from Earth, you're basically looking along the edge of a cosmic blade. Near equinox, when Uranus's day-night line runs almost straight through the middle, the geometry lines up just right. The rings swing edge on to the Sun, into our line of sight. In telescopes, they can nearly vanish. They're already dark material reduced to a nearly invisible hairline. But that's also when they become surgical tools. As the planet and rings crawl past background stars, each ring carves sharp, timed cuts in the starlight. Those occultations let us measure ring widths, gaps, and even clumps that no camera could resolve. And the seasons don't stop at visibility. They change how the rings themselves are lit. During solstices, one ring Ansa bakes in continuous sunlight, while the opposite side spends years in a kind of low-angle dusk. Different parts of the same narrow band get different doses of solar energy over the Uranian year. That can tweak ring particle temperatures, recharging charged dust, nudging tiny grains along magnetic field lines, and feeding faint, ghostly ring arcs that appear more clearly under certain lighting. So the broken seasons of Uranus don't just paint its atmosphere, they rewire the lighting for the entire miniature system orbiting with it. Rings, moons, magnetosphere, all taking turns in and out of the spotlight as this tilted world rolls around the sun. The question is, when those dim rings shift their glow, what does that do to the dark, frozen moons hiding just beyond them? Those dark, frozen moons, they're not just bystanders. They're trapped in the same sideways geometry, riding along with the broken seasons that rewired Uranus' sky. Now let's begin with the family portrait. Zoom in past the rings and you meet the major moons: Miranda, Ariel, Umbriel, Titania, Oberon. You know the one, a neat little chain of icy worlds, each one orbiting close to Uranus' equator. But that equator is tilted about 98 degrees to the plane of the solar system. So their normal orbit is actually a cartwheel path, turned almost completely on its side relative to the sun. Because here's what nobody tells you. When Uranus rolls, its moons roll with it. Their orbits are aligned to the planet's equator, not to the flat orbital plane we like to draw in diagrams. So from the sun's point of view, these moons aren't politely circling in a thin disk. They're looping through a wildly tipped track, taking turns being plunged into decades of darkness or bathed in decades of low, glancing light. Imagine standing on Titania. For one part of Uranus's 84-year orbit, the sun just circled the horizon, barely rising, barely setting, for something like 21 Earth years. Then as Uranus moves along its path, the whole lighting scheme slowly inverts. Seasons here aren't gentle tilts. They're full-body rotations of the entire system. And yet, something is above the planets. Something is below them. In this picture, above and below are measured from a sideways equator, not the solar system's usual reference plane. That alignment is a giant clue. If Uranus had been knocked over after its moons were already in place, we'd expect them to keep their original, more ordinary orbits around the old equator, ending up misaligned with the new tilt. Instead, they're locked into the 98-degree geometry. The simplest explanation? The tilt came first, then a disk of debris formed around the wounded planet, and the moons condensed out of that disk, inheriting the new, sideways equatorial plane from birth. So, these worlds are not just companions, they're evidence. They remember the orientation of the impact, even if they've forgotten the details. And then there's Miranda. This tiny moon looks like it was hit with a cosmic patch tool. Giant canyons, mismatched terrains, jigsaw blocks that don't quite line up. One idea is that intense tidal forces tore Miranda apart and then gravity reassembled it, scrambling the surface into that bizarre collage. In a tilted kingdom with shifting gravitational tugs and evolving orbits, that kind of violence suddenly feels less like an exception and more like part of the script. If the rings are warped and the moons are scarred, all by the same ancient event that broke Uranus's seasons, then what about the planet itself? What deeper fractures, hidden layers, or tilted cores might still be lurking beneath those pale blue clouds? To find those fractures, you have to dive past the rings and the clouds and drop into a planet that doesn't just spin sideways. It's built sideways on the inside too. Now, let's begin with the basic picture. Uranus looks like a smooth pale blue cue ball from a distance, but under that calm face it's layered like an onion under extreme gravity. At the very center, we think there's a relatively small rocky core, a compressed mix of silicates and metals, only a few Earth masses across. Wrapped around that is the real bulk of the planet, a thick mantle of so-called ices, water, ammonia, methane, crushed into exotic phases under millions of atmospheres of pressure. More like a hot, slushy mineral than the frozen ice cubes you're picturing. Outside that mantle sits a comparatively thin envelope of hydrogen and helium. That gas layer is shallow by giant planet standards, just a frosting compared to Jupiter's deep atmosphere. But it's the part you see when you look at those blue clouds. So, let's start at the very beginning of the mystery. If Uranus is built so much like Neptune, why does it behave so differently? Because here's what nobody tells you. Inside Uranus is weirdly quiet. Neptune glows in the infrared, radiating nearly twice as much energy as it gets from the sun. Uranus, it barely leaks any extra heat at all. Its internal heat flow is so low that it's one of the coldest planets in the solar system, with cloud-top temperatures dipping below those of more distant Neptune. How does a giant planet end up so thermally bored? One leading idea points straight back to that ancient collision that knocked the whole world on its side. A glancing off-center impact big enough to tilt a planet by 98 degrees doesn't just twist the orbit and walk away. It could have shattered and reassembled the interior, mixing some regions while leaving others stratified, and crucially, it could have locked heat into deep layers, shutting down large-scale convection that would normally carry energy outward. Imagine a pot of soup that gets stirred once, violently, and then left to sit for billions of years. If Uranus's interior is layered and sluggish like that, its seasons don't just play out in the clouds. They sink in, slowly. When one pole stares at the sun for decades, that energy has to percolate through a stratified mantle that resists mixing, so the climate response can lag behind the sunlight by years or even whole seasons. You get a sideways planet whose weather and temperature patterns are always slightly out of sync with its orbit, like a world permanently jet-lagged. And yet, something is above the planets. Something is below them. In Uranus's case, that strange, layered interior doesn't just warp the seasons. Maybe twisting space around the planet itself, giving rise to one of the most broken, lopsided magnetic fields in the entire solar system. So if Uranus's interior is already bending the rules, its magnetic field just goes ahead and ignores the rulebook entirely. On most worlds, the magnetism behaves. Earth's magnetic field, for example, is tilted a little, but it's still roughly lined up with our spin axis and anchored near the core. You get this fairly symmetric magnetic bubble around the planet, a magnetosphere that wraps around the solar wind like a smooth, invisible shield. You know the one. Neat field lines arcing from one pole to the other, like a bar magnet living right in the middle. Because here's what nobody tells you. That tidy picture is the exception, not the rule. It works well enough for Earth, for Jupiter, for Saturn. Their fields are close to centered, close to aligned, So when they spin, the whole magnetic structure just turns like a well-balanced top in space. Uranus does not turn like a well-balanced top. Its magnetic field is tilted about 59 degrees away from its rotation axis. Not a polite little lean. A full, neck-cricking twist. And on top of that, the whole magnetic source is shoved off to the side, displaced from the planet's center by roughly a third of Uranus's radius. Imagine holding a rubber ball and hiding a bar magnet inside it, but you don't put the magnet in the middle. You ram it off toward one edge and then twist it so it points in some random direction. That has almost nothing to do with how the ball is spinning. Now spin the ball. Fast. While the whole thing orbits the sun sideways. That's Uranus. Its magnetosphere isn't a clean, symmetric bubble. It's a lopsided, warped magnetic cloud trailing the planet through space, with regions where the field is much stronger on one side and much weaker on the other. As Uranus rotates, that crooked off-center field sweeps around, so the strong side and the weak side keep trading places relative to the sun and to the flow of solar wind. So, let's start at the very beginning of the weirdness this creates. One part of the magnetosphere might be puffed up and pushed back by the solar wind, while another part is compressed and hammered. And then half a rotation later, those roles are reversed. It's like watching a magnetic balloon being squeezed from different angles every few hours, on a planet whose poles already take turns staring at the sun for 42 years at a time. What does summer even mean for charged particles in a field like that? How do auroras behave when the magnetic poles don't match the spin poles or the geometric center, when the whole system is rolling around the solar system's flat orbital plane? Now let's begin to follow those particles and see how broken seasons look when you're made of plasma instead of air. So those particles leave the sun, racing through space in a pretty steady wind. Then they hit Uranus. And the whole idea of a normal magnetosphere just falls apart. Because here's what nobody tells you. Uranus doesn't just tilt its spin axis. It also tilts its invisible magnetic umbrella even more. The planet is rolled about 98 degrees relative to the solar system's flat orbital plane. But its magnetic field is tilted another 59 degrees from that spin and shoved off-center by about a third of a radius. So as Uranus orbits once every 84 years, the angle between the solar wind, the spin axis, and the magnetic axis is constantly changing in this three-way, off-balance dance. On Earth, the magnetic poles wander a bit, sure, but they roughly point along the spin axis. You know the one. Neat textbook picture. Dipole field. Auroras near the poles. At Uranus, there are times in the orbit when a magnetic pole is almost staring straight at the sun, like a spotlight pointed into the solar wind. Half a season later, that same pole can be twisted off to the side or even rotated away, hiding in the planet's magnetic night. What does that do to space weather? It means that the way charged particles stream in and get trapped is wildly seasonal in a way we don't see in the inner solar system. When a magnetic pole faces the sun, solar wind particles can pour down those field lines, lighting up intense, localized auroras and hammering one hemisphere with particle bombardment. As Uranus rolls along its orbit and the geometry shifts, that axis shuts off, the other pole swings into a better position, and the whole magnetosphere reconfigures. Here's the twist inside the twist. Because the field is offset from the center, one hemisphere can sit closer to the strongest part of the magnet, while the other is left under a weaker, more stretched field. So depending on the season, one side of Uranus can get brighter auroras, deeper radiation belts, and more energetic particle rain than the other. It's like giving one pole a space weather monsoon and the other a long, charged particle drought. And yet something is above the planets. Something is below them. In this case, above and below that tilted magnetic plane keep flipping as Uranus rolls. So the region where particles are funneled in literally migrates around the planet over decades. So let's start at the very beginning of our data problem. We saw almost none of this in action. Voyager 2 flew past in 1986, catching Uranus near southern summer solstice when the South Pole was pointed at the sun. That was one frozen frame of a magnetosphere mid-contortion, not the full movie. Now we're trying to model 84-year magnetospheric seasons from a single snapshot. Uranus doesn't just have broken sunlight seasons, it has broken space weather seasons. And those seasons may be rewriting how its rings, atmosphere, and even potential moon surfaces evolve over time. So if Uranus's space weather is broken, the next question is brutal. What kind of engine is driving a magnetosphere that crooked in the first place? To get there, we have to zoom inside the planet. Because here's what nobody tells you when you see those neat bar magnet field lines drawn through a blue-green sphere. Planetary magnetic fields are not decorations. They're dynamos. You're looking at the fingerprints of moving, electrically conducting fluids buried deep below the clouds, twisting under gravity and rotation. On Earth, that dynamo lives in a molten iron core, almost perfectly centered. The whole picture is pretty tidy. Spin the planet, stir the metal, generate a field that's roughly aligned with the rotation axis and anchored at the center. So when you see Earth's magnetic poles wander, they drift. They don't teleport. Ice giants do not play by those rules. Now let's begin with the weirdest part. In Uranus and Neptune, the best models say the dynamo doesn't live in a central metal core at all. It wakes up in a shell of exotic, conductive material somewhere in the middle layers. Hot water, ammonia, and methane crushed into supraonic phases, where hydrogen atoms roam like an electrical ocean through a crystalline lattice. Imagine a conducting donut floating inside the planet instead of a solid core at the center. You know the one, the kind of picture where, the moment the dynamo moves off-center, the field lines start to look like they've been yanked sideways. Shift the engine and the magnet has no reason to stay straight. An off-center, lopsided dynamo naturally produces a field that's tilted, skewed, and spatially offset from the planet's center. For Uranus, that means a magnetic axis tipped about 59 degrees from the spin axis and displaced by roughly a third of its radius. That's not a small design flaw. That's a whole different blueprint. So where does the ancient violence come in? So let's start at the very beginning of Uranus's weirdness. A 98-degree axial tilt screams, colossal impact. A glancing blow from a protoplanet early in the solar system's history could have knocked Uranus onto its side and, crucially, scrambled its interior. Instead of a smoothly convecting mantle, you get layers. A stratified interior where heat leaks through a relatively thin, off-center shell becomes the perfect place to park that conducting donut. In that picture, the impact didn't just tip the spin axis, it rearranged the geometry of the dynamo itself. The planet's rotation, the direction of heat flow, and the conducting layer's shape no longer line up. So the field ends up crooked because the internal plumbing is crooked. And here's the twist. Neptune's field is also wildly tilted and offset. 2 planets, 2 broken magnets. That hints that ice giants, with their thick mantles of conductive ices, might naturally favor weird magnetism, even without a sideways spin. Put it all together, and a single story emerges. Uranus's broken seasons, broken spin, and broken magnetic field are all symptoms of the same deep misalignment. A world whose internal and external geometry never fully recovered from early chaos. The next step is to ask what that chaos did to everything orbiting around it. So let's take that chaos and move in. Not with a telescope this time, but with a boarding pass. Now let's begin with a floating research station, suspended in Uranus's upper atmosphere at mid-latitudes. You're in a ringed habitat, buoyed by hydrogen balloons in a pale blue haze, high above pressures that would crush you. Outside the window, the sun is a tiny white coin. It still rises, it still sets, and your day is a brisk 17 hours long. At first, it feels almost normal. The sun arcs low across the sky, dips below the horizon, and the soft twilight of scattered methane light takes over. You eat, you sleep, you run experiments. You get used to the rhythm, because here's what nobody tells you. On Uranus, the weirdness doesn't hit you in a single dramatic moment. It sneaks up on you year by year. Watch the sky long enough, and the sun's path starts to drift. Each orbit around the sun takes 84 Earth years, so the seasons crawl. Over a decade, that little white disk climbs higher each noon, stretching daylight, shaving minutes off the night. Over another decade, it sinks, day after day, until the sun barely clears the horizon at noon, and your station spends most of its 17-hour rotation in a kind of permanent sunset. You live through a summer that lasts 20 years. You live through a winter that lasts 20 more. The calendar on the wall looks like it belongs to you, but the real calendar is written in the angle of that tiny sun against the tilted plane of Uranus's orbit. And the light isn't the only thing that has seasons. The magnetosphere does too. The planet's magnetic field is tilted almost 60 degrees from the spin axis and shoved off center. So as Uranus rolls around the sun, your station drifts in and out of warped magnetic lobes. Some years, you're under a relatively quiet sky. Other years, you pass beneath crackling auroral ovals that sweep across the atmosphere like slow-motion curtains. You step to the viewport and see arcs of green-blue light, tracing the invisible field lines, brightening and fading over months. Charged particles rain down more intensely in some eras than others. Your radiation shields and power systems are designed around cycles that last longer than a typical Earth career. Now compare that to a polar outpost. You know the one, a lonely tower near the North Pole, where sunrise is a once-in-a-lifetime event. For roughly 42 Earth years, that crew lives in unbroken daylight, the sun circling their sky without ever setting. The next crew inherits the opposite, 42 years of night, lit only by stars, rings, and auroras. On Uranus, mission planners don't ask what the weather will be next month. They ask what the sunlight will be for the next generation. Because once you stretch seasons across human lifetimes, the calendar stops being a cycle and turns into a series of eras. And yet, something is above the planets. Something is below them. The real question is what those eras do to everything caught in Uranus's tilted gravitational reach. So before Uranus finishes breaking your intuition, we need to shrink something you think you know. Your seasons. Because compared to what's happening out there, Earth's entire climate cycle is just a quick shiver. So, let's start at the very beginning. Earth is tilted about 23.5 degrees relative to the plane of its orbit. You know the one, the neat, textbook picture with a little leaning globe and the 4 labeled seasons. 1 year's 365 days, and we slice it into 4 chunks of roughly 3 months each. Summer, autumn, winter, spring. Rinse, repeat. No matter where you live, the sun still rises and sets every single day. At the equator, it's nearly 12 hours of day and 12 of night, all year. At mid-latitudes, the days stretch in summer and shrink in winter, but the rhythm never stops. Only if you go to the extreme poles do you get a taste of continuous day or night. And even there, it's measured in months, not decades. Now zoom back out and put Earth next to Uranus. Visually, the difference is brutal. Earth is a modestly leaning globe, a polite nod away from straight up. Uranus is a nearly horizontal spinner, a planet that's been knocked so far over its tilt is about 98 degrees. If you draw both as spheres on the same orbital plane, Earth looks slightly relaxed. Uranus looks like it's lying down on the job. Because here's what nobody tells you. In that context, Earth's tilt is tiny. Our seasons feel huge because we live inside them. But geometrically, they are small ripples in the sunlight compared to the tidal wave Uranus gets when a pole points almost straight at the sun for 42 years. On Earth, a harsh winter might last a few months. A freak heat wave, a few days. Then the planet turns. The sun climbs higher or lower in the sky, and the anomaly reverses. The whole system is built on rapid, reversible perturbations. We talk about multi-year droughts or El Niño cycles, and they sound long, but they're still riding on a 1-year baseline that never stops cycling. Even our invisible seasons are gentle. Earth's magnetic field is fairly well aligned with its rotation axis and reasonably centered in the core. That means our space weather has seasons, but they're subtle. Auroras creeping farther from the poles, tiny shifts in radiation belts, a bit more geomagnetic activity when the sun's cycle lines up just right. Now put that next to Uranus's magnetosphere, tilted almost 60 degrees from its spin and offset from the planet's center. Its magnetic seasons swing wildly as it orbits, while hours barely wobble. So what feels normal to you, annual cycles, quick transitions, modest tilts, is actually a narrow, lucky configuration. The solar system has no problem building planets where the tilt, the sunlight, and the magnetic field all refuse to line up. The real question is what normal even means once we stop using Earth as the default. So if normal doesn't mean Earth, we have to ask a slightly uncomfortable question. Is Uranus really the oddball here? Or are we the ones with the weird, boring seasons? For most of human history, we didn't even get to ask that. You had the sun, you had the wandering stars, and then eventually you had this neat set of 8 planets. That was the entire sample size. In that tiny catalog, a world rolling around the sun on its side looked like a once-in-a-universe accident. Of course, Uranus felt like the fluke. What else were you going to compare it to? Because here's what nobody tells you. That picture collapsed the moment we started finding planets around other stars. Once exoplanet surveys came online, the sky stopped being a backdrop and turned into a census. Thousands of worlds, orbiting thousands of suns. Hot, cold, dense, puffy, scorched, frozen. And suddenly our 8-planet solar system looked less like the rule and more like one strangely tidy example. Now let's begin to zoom out. When telescopes like Kepler and TESS stare at a patch of sky, they keep finding planets that are about the size of Neptune and Uranus. Over and over, these ice giant class worlds show up close to their stars, far out, packed into tight systems, spread across wider orbits. If you were an alien astronomer making a highlight reel of common planet types, you'd probably put Uranus-ish Worlds near the top. Earth-sized, Earth-tilted, Earth-seasoned planets. Those might be the niche art film category. And the orbits? They're not politely aligned the way our textbook diagram suggests. Some exoplanets whip around their stars on paths tilted wildly compared to the star's spin. Some even go retrograde, orbiting backwards relative to the star's rotation. You know, the one tidy solar system picture where everything circles in one flat, obedient plane. The universe keeps sending us counterexamples. So if orbits can be misaligned and spins can be tipped, why should Uranus' 98-degree tilt be shocking? A sideways ice giant with broken-looking seasons might not be a cosmic joke. It might be business as usual. In a galaxy full of ice giants, a planet that spends decades with one pole staring at its star could be more representative than our upright, modestly tilted Earth. And yet something is above the planets. Something is below them, not in the sense of up and down in space, but in the sense of what we call normal versus broken. What if our entire definition of broken seasons is just not like Earth, and Uranus actually belongs to a very common planetary archetype? If that's true, then our mild yearly cycle is the real outlier, which raises one last question before we dive back into Uranus itself. If sideways seasons are common, what does that do to weather, to atmospheres, to the long-term fate of a world? So if Uranus isn't the weirdo, how many sideways worlds are we actually missing? Here's the twist. Measuring a planet's tilt directly is incredibly hard once you leave the solar system. We can't just zoom in and watch an exoplanet spin. What we can do is look at the alignment between the star's rotation and the planet's orbit and use that as a clue. If the orbit is wildly misaligned with the star's equator, the planet's spin has probably had a chaotic history too. Because here's what nobody tells you. We already know of systems where the solar system as a flat disk picture has been completely shredded. Hot Jupiters that skim right above their stars can orbit at steep angles, even backwards, compared to the star's rotation. You know the one, that tidy textbook diagram with the star in the middle and neat circular paths all in the same plane. In a lot of exoplanet systems, gravity has thrown that diagram out the window. We've watched stars wobble and dim in ways that tell us their close-in giants are on tilted orbits, sometimes more than 90 degrees off. That means the planet's orbital plane is leaning, even rolling relative to the star's equator. And yet, something is above the planets. Something is below them. There is a reference plane in each system, and these worlds are flagrantly ignoring it. If orbital planes can be that broken, do you really think planetary spins are all politely lined up like Earth's? Now let's begin to connect this to impacts. In our own solar system, we think Uranus got its 98-degree tilt from a colossal collision. If giant impacts are just part of how planets grow in a crowded protoplanetary cloud, then every ice giant, every super-Earth, every mini-Neptune out there has had a chance to get smacked sideways. You don't need a unique accident. You just need a busy young system and time, so picture the climates that follow. On a Uranus-like world, one pole could stare at its star for decades, while the other drowns in darkness. Long, slow seasons that are less spring, summer, fall, winter, and more half a lifetime of dawn, half a lifetime of midnight. What does that do to an atmosphere? To winds, to clouds, to oceans that might only see sunlight every few decades? Life, if it ever emerges there, would have to ride out swings that make our ice ages look like long weekends. And this is where Uranus suddenly looks less like a punchline and more like a local laboratory, a nearby prototype for a whole class of sideways worlds whose seasons we can't yet watch in detail. Because once we decode how gravity, tilt, and climate interact on this rolling ice giant, we're not just explaining one oddball planet. We're building the playbook for thousands of invisible, broken season worlds orbiting other suns. The real question is, what hidden patterns are those worlds following that Uranus is already trying to show us? So if Uranus is already our test case for broken seasons, there's a brutal follow-up question hiding underneath that picture. Could anything actually ride out a year where winter is 42 Earth years long? Now let's begin with the honest part. We have zero evidence of life on Uranus. No fossils, no microbes, no little sky whales flapping through the methane clouds. But the planet gives us a laboratory in our heads. Because here's what nobody tells you. Even when a world looks hopeless by Earth standards, its extremes are exactly what let us probe the outer limits of habitability. Start with where life would have to live, not on a solid surface. Uranus probably doesn't have one in any way you'd recognize. You'd be out in the atmosphere, or in some hypothetical floating ocean layer, where water, ammonia, and other volatiles mix under high pressure. Imagine an entire ecosystem suspended in a twilight soup, while above it the poles swing from decades of daylight to decades of darkness. What does a 42-year polar night do to biology? On Earth, even Arctic winters push organisms to the edge. Yet we see strategies. Tiny zooplankton in polar seas drop into deeper, more stable water when the surface freezes and the sun disappears. Seeds and spores sit dormant in permafrost for years, their chemistry slowed almost to a stop, then wake up when light and liquid water return. Under Antarctic ice, microbes live in briny pockets that barely change at all, ignoring the seasons raging above. Now scale those tricks up to Uranus. You could imagine atmospheric microbes that ride vertical winds, sinking down to warmer, more stable layers when their hemisphere tips into the long dark, then drifting upward again when the sun finally crawls back over the horizon. Or long-lived spores that endure entire seasons as microscopic time capsules, with active generations separated by decades of chemical hibernation. Energy is the real killer. What do you eat when the sun vanishes for half a century? On Earth's deep seafloor, entire communities run on chemical gradients at hydrothermal vents, tapping into planetary heat instead of starlight. Under thick ice shells, microbes use oxidants trickling down from above and reductants welling up from below. You know the one consistent rule? If there's a stable gradient, life will try to exploit it. So on Uranus, you'd look for chemistry in those layered clouds, where vertical mixing and exotic molecules create slow, steady energy leaks that hypothetical organisms could store, hoard, and stretch across the long winters. And yet something is above the planets, something is below them. We're used to drawing a flat solar system where habitable hugs a narrow band near Earth's orbit. Uranus forces us to tilt that plane in our minds and ask a harder question, not just where liquid water can exist, but where adaptation could keep going when seasons themselves are broken. Because once you let that idea in, this sideways ice giant stops being just a weirdo and starts looking like a prototype for life on thousands of tilted storm-wrapped worlds we haven't even seen yet. So here's the uncomfortable part. For all the drama we've just painted onto this sideways world, we've only ever seen Uranus up close once. You know the one. Voyager 2, 1986, a single high-speed flyby that lasted a few hectic days after a journey of nearly a decade. It caught Uranus right near southern summer solstice, when the South Pole was tipped toward the sun and the North was locked in decades of darkness. Our entire close-up picture of those broken seasons, frozen around that one seasonal moment. Because here's what nobody tells you. When you look at those pale blue images in textbooks, you're looking at a very specific season from a very specific angle with a spacecraft that never slowed down. Voyager 2 didn't orbit. It just barreled through the outer solar system on a gravity-assist grand tour. Jupiter, Saturn, Uranus, Neptune, and out. No second chances. No coming back half a Uranian year later to see what changed. Why haven't we gone back? Distance, time, and power all gang up on you. Uranus orbits about 19 times farther from the Sun than Earth. So even with a favorable alignment, you're looking at a cruise of more than a decade for a heavy orbiter. Its year is 84 Earth years long, which means each season lasts around 21 years. To really watch those poles swing from endless day to endless night, you're talking about a mission that has to survive and keep its instruments warm and powered across a giant chunk of a human lifetime. Solar panels? At Uranus, sunlight is so weak that you'd need absurdly large arrays just to run the heaters, let alone the cameras. So you're forced into nuclear power sources, precision, gravity-assist trajectories, and navigation that has to be right the first time. A little miscalculation in deep space, and your beautifully planned orbit becomes a very expensive flyby. So, let's start at the very beginning of how we've filled in the gaps. Most of what we know about Uranus's seasonal changes comes from watching it from far away, year after year, with Earth-based telescopes and space observatories like Hubble and JWST. Astronomers have stitched together slow changes in cloud bands, storms that flicker into existence near equinox, and rings that brighten or fade as the planet's tilted plane shifts with respect to us. It's like trying to understand a movie by catching one frame every few months. That's why proposed Uranus orbiters and atmospheric probes are such a big deal. Park an orbiter there for even 10 or 15 Earth years, and you'd watch nearly an entire season unfold. You could dive a probe into the atmosphere to taste the chemistry that drives those muted storms, fly repeatedly through the rings, and map how that lopsided magnetosphere twists as the planet rolls around its orbit. Without that, Uranus stays a set of tantalizing snapshots, a broken season world we glimpse from across space, but never truly watch in motion. And yet, something is above the planets. Something is below them. To really see where Uranus fits in that three-dimensional picture, we have to get back out there. So what does getting back out there actually look like? Not another quick flyby that blinks past Uranus in a day, but a patient orbiter that lives through its broken seasons and watches them unfold in real time. Now let's begin with the hardware. You send a spacecraft all the way to the edge of the solar system. You don't just bring one camera and hope for the best. You pack a magnetometer on a long boom to feel every twist of that tilted field. You mount infrared eyes to read temperature patterns in the dark, and radio instruments to listen to lightning, auroras, and the crackle of charged particles in its warped magnetosphere. You give it high-resolution cameras to zoom in on the rings and moons, and you tuck away deployable atmospheric probes waiting to dive. Because here's what nobody tells you. Uranus's weirdness only makes sense when you watch it change. An orbiter staying for a decade or more could track the slow drift of storms as the planet crawls through its 21-year seasons. You'd see bright methane clouds pop up, fade, and migrate with the changing sun angle. You'd watch the polar regions go from decades of daylight toward dusk and measure how the temperature structure lags behind the light, revealing how deep the seasons actually penetrate. Long-term monitoring means we finally get a weather report, not a postcard. How fast do those jet streams really blow when one pole is pointed almost straight at the sun? Do cloud bands reconfigure as equinox approaches, or do they snap into a new patterns like a climate switch being thrown? A flat diagram of the orbit can't tell you that. Only a time-lapse from up close can. Then there's the magnetic field. Remember, it's tilted about 59 degrees from the spin axis and offset from the center. So as Uranus rotates and orbits, its magnetosphere doesn't just wobble. It tumbles through space in a bizarre, seasonally driven dance. An orbiter threading through that field on different orbits could map its shape in 3 dimensions. Watch how the solar wind carves it, and see how magnetospheric seasons play out when nothing lines up the way it does on Earth. And yet, something is above the planets. Something is below them. To really feel the climate, you have to go in. Dropping an entry probe into the atmosphere at different latitudes and different seasons would give direct samples of composition, winds and thermal structure. From the hazy cloud tops down into the deeper layers where the real heat budget is decided. How does the sideways tilt change the vertical mixing? Where do those mysterious hazes form? Here's the twist. That data wouldn't just explain Uranus. It would become a Rosetta Stone for the ice giants we see as single pixels around other stars. When we watch an exoplanet dim its star in infrared, or see a hint of methane in its spectrum, we'd finally have a physical, 3-dimensional picture to compare against. Does a 98-degree tilt always mean shredded seasons and a lopsided magnetosphere? Or is Uranus the outlier in a much stranger family? Because once you can decode one sideways world in detail, you can start asking a much bolder question. In the vast, not-so-flat cloud of planets in our galaxy, which ones are hiding Uranus-level weirdness that we haven't even learned how to see yet? So here's the twist. The moment we call Uranus sideways, we've already picked a favorite direction in space and quietly crowned Earth as normal. Because here's what nobody tells you. There's no official up in the solar system. There's no cosmic arrow stomped on the universe saying, this way is correct, that way is weird. In space, there is no up, there is no down. There are only planes, rotations, and the diagrams we draw to keep our brains from melting. Astronomers survive this chaos by making agreements. We define a north pole for a planet as the end where the rotation follows the right-hand rule. We define an orbital plane, like Earth's path around the Sun, and call that the ecliptic. Then we say things like above the plane and below the plane, as if we were talking about a table and a floor, not a glowing ball of gas and a tilted ice giant in a 3-dimensional cloud of orbits. Now let's begin to mess with that intuition. Imagine we decide that Uranus gets to be the reference. Its spin axis, tilted about 98 degrees from the ecliptic, becomes our gold standard for up. Suddenly Earth, with its polite 23.5 degree tilt, isn't the baseline. It's the one that's leaning. In this picture, our seasons start to look like the odd, restrained version of Uranus's decades of daylight and darkness. Not the other way around. Push it further. What if, instead, we define up using Uranus's equator, the way we often do with Earth? Now the whole solar system seems skewed. The familiar flat diagram you grew up with. You know the one, with the planets on a tidy horizontal line? Rotate that so Uranus's equator is horizontal, And suddenly Mercury through Neptune are all running around on a slanted track, like someone bumped the cosmic whiteboard. And yet something is above the planets. Something is below them. But those words only make sense once we've picked a plane, usually Earth's orbital plane, and frozen it into the picture. Diagrams quietly choose that frame, then your brain does the rest, filing Earth under normal and Uranus under broken, without ever asking, broken compared to what? So the real question isn't, why is Uranus wrong? It's, why did we decide this one particular orientation was right? From the universe's point of view, Uranus isn't misbehaving. Its 98-degree tilt, its extreme seasons, are just gravity and geometry playing out after some violent ancient encounter. So, let's start at the very beginning of that story next. What kind of impact does it take to rewrite a planet's idea up and down? But before we rewind to that ancient impact, we need to talk about something much closer to home, the picture in your head. Because here's what nobody tells you. The most powerful object in this whole story isn't a telescope or a supercomputer. It's that flat solar system diagram you met in elementary school. You know the one. The neat, clockwork orbits. The planets evenly spaced like beads on a wire. All the little spheres standing politely upright as they circle the sun in a razor-thin plane. It feels orderly, safe. It whispers, "This is how a solar system is supposed to look." Now let's begin tearing that picture apart. Not because it's wrong, but because it's incomplete. Those diagrams are tools, not truths. They exaggerate what's convenient. Orbital order, relative distance, who's inside and who's outside, and they quietly erase what's messy. Like the 3D thickness of the planetary disk, or the fact that Uranus is basically rolling around the sun on its side. When every planet in your textbook is drawn straight up and down, your brain gets biased. It starts to think a big tilt must be rare, or unstable, or a mistake. So when you meet Uranus with its 98-degree tilt and 42-year seasons of daylight and darkness at the poles, it feels like a glitch in the matrix instead of a natural outcome of gravity and collisions. But the universe doesn't care about our diagrams. In real space, each planet is more like a spinning top, leaning at its own angle to the orbital plane. Earth is tipped by about 23 degrees. Mars leans a bit more. Saturn is a dramatic 26 degrees. Neptune is 28. And Uranus is the kid who took lean as a personal challenge. So, let's start at the very beginning of your mental model and upgrade it. Don't imagine a flat poster where everything stands upright. Imagine a slightly warped disk of orbits, with each world as a tilted top, whirling through space. Some tilts are modest, some are extreme, and they all just keep going, year after year, because gravity doesn't demand upright, it only demands balance. And yet something is above the planets. Something is below them. Not in an absolute sense, but relative to that shared orbital plane, the invisible sheet defined by their paths. Once you picture that, Uranus stops being the broken one and becomes a clue that the whole system is three-dimensional, layered, and alive. Because once you upgrade that flat picture, everything changes. Seasons stop being a simple tilt demo with a flashlight and a globe, and start becoming a spectrum of possibilities. The question is no longer, why is Uranus so weird? But what else can a solar system do? Hold on to that new image, because now we can finally ask, what kind of collision can twist a spinning top that far without tearing it apart? So that collision twists Uranus over, and suddenly seasons stop being about weather and start being about geometry, pure geometry, not clouds, not storms, not winter is cold, summer is hot, but angles in space between a spinning axis and a distant lamp. Now, let's begin with the simplest version of that picture. Forget the whole solar system for a second. In your room, you put a lamp on a table. That's the sun. Then you take two globes on little stands. One is Earth, tilted about 23 degrees. The other is Uranus, tilted almost 98 degrees. So far over, it's basically lying on its side. You keep both globes on the same flat circular track to mimic the orbit. Because here's what nobody tells you. Seasons are just. What angle is the sun hitting this spot right now? And for how long each day? On Earth, as we carry that tilted globe around the lamp, the North Pole leans toward the light for part of the orbit and away for part of the orbit. The solar elevation changes. The day length stretches and shrinks, but never to absurd extremes. You always get sunrise. You always get sunset. Even the poles get only months of darkness, not decades. Now spin the Uranus globe. Same lamp, same orbit, same gravity holding the whole picture together. The only thing you've changed is the tilt of the axis relative to the orbital plane. And yet something is above the planets. Something is below them. Suddenly, during solstice, one pole is staring almost straight into the bulb while the other is turned almost perfectly away. One hemisphere is locked in noon for roughly 42 Earth years. The other is locked in midnight for 42 years. That's not a different kind of physics. That's just the same equation with a wilder input angle and a much longer year. You can literally see it with your desk demo. When the sideways globe has its pole aimed at the lamp, the entire polar cap is in continuous light. Spin the globe and nothing changes. It just pirouettes in daylight. Slide it a quarter of an orbit around the lamp, and now the equator is getting the most direct hit. Days and nights even out, and the planet briefly behaves more like Earth. Another quarter, and the opposite pole is the one roasting. So, let's start at the very beginning of a new intuition. Seasons are the geometry of spin versus sunlight, scaled by orbital period. Once you think that way, Uranus stops being a freak and becomes a template. You can look at an exoplanet with a guessed tilt of 60 degrees or 120 degrees and already sketch in your mind when its poles burn, when its equator freezes, and how long each extreme lasts. And if a simple lamp and globe can predict decades of daylight on Uranus, what happens when we add the next twist? A magnetic field that refuses to line up with any of this. So if Uranus's geometry can be sketched with a lamp and a globe, the part that really breaks your brain isn't the angle, it's the clock. Because here's what nobody tells you. On Uranus, the calendar is the alien. One Uranian year is about 84 Earth years. That means each season lasts roughly 21. A summer that starts before you're born can still be going strong when you're retiring. A winter can swallow your entire childhood. You don't grow up through the seasons. You grow old inside one of them. On Earth, you carry all four in your memory. You know the one, the first hot day that feels like summer, the first leaf that really looks like autumn, the first snow that makes the world go quiet, the first spring rain that smells like relief. Our sense of climate is stitched together from those repeating loops. A year is long enough to feel complete and short enough to repeat. Now stretch that loop to 84 years. Imagine you're born near Uranian spring. The sun is just beginning its decades-long crawl toward your hemisphere's pole. You grow up under a sky where the sun slides higher, year after year, but never comes back down in any way your body recognizes. By the time it finally does, You're old enough that children are asking you what the last low sun was like, and you have to reach back to memories from before you could read. So, let's start at the very beginning of what that does to culture. On Uranus, summer and winter aren't personal experiences. They're historical events. You don't say, last winter we had a big storm. You say, my grandparents told me about the winter before this one. Traditions have to be engineered to survive across generations because no one person ever sees the full cycle. Because once your seasons are longer than a human life, language breaks. Words like annual, yearly, every winter stop meaning what they mean here. You can't promise to do something next year when that's functionally the rest of your life. Planning becomes a multi-decade negotiation with gravity and orbit. Festivals might be named after positions of the sun that nobody alive actually remembers seeing. And yet, something is above the planets. Something is below them. It's our perspective. We pretend the solar system runs on an Earth clock with our neat 24-hour days and 365-day years as the baseline, the flat reference plane for time itself. But out here, those units are parochial. They're local slang. So ask yourself, how would your memory feel if the sun's slow rise and fall across your sky unfolded, not over months, but over decades? What would childhood mean if your first real sunset of the season happened at 40? What would you pass down to people who will live their entire lives under a different tilt of light than yours? Now, let's begin to complicate that even more. What happens when the planet's magnetic seasons refuse to match the sunlight at all? So at this point, Uranus looks less like a planet and more like a physics thought experiment that escaped the lab. Sideways spin, poles that take turns staring straight into the sun for 42 years, then hiding in unbroken night for another 42. A magnetic field tilted almost 60 degrees away from that spin and shoved off center. Faint, tilted rings, barely any internal heat leaking out at all. It's like someone hit randomize on every setting and then left it in the solar system to confuse you on purpose. Because here's what nobody tells you. For a long time, each of those quirks was treated as a weird exception. A one-off. The sideways one. The boring blue one. The magnetically misaligned one. The planet we quietly filed under odd so we could keep our mental picture of neat, upright, well-behaved worlds. Then we started finding exoplanets. Thousands of them. Suddenly, normal began to melt. We found hot Jupiters skimming their stars in days, worlds on stretched, looping orbits, planets whose entire orbital planes are tilted wildly compared to their stars' spin. We've measured stars whose planets seem to roll around them on inclinations that would make Uranus feel seen. We've seen hints of interiors with exotic layers and broken magnetic fields that don't line up the way Earth's does at all. So, let's start at the very beginning of this idea of normal. You grew up with Earth as the template, a modest 23.5 degree tilt, a year that fits inside your calendar. A magnetic field mostly aligned with the spin, close enough that you can pretend the bar magnet diagram in school was telling the whole truth. It feels reasonable to assume that's the baseline. But what if it isn't? What if our comfortable, temperate, 12-month orbit is the strange case? What if a planet that doesn't roll on its side, doesn't bake one pole for decades, doesn't have a magnetic field doing acrobatics in its own sky is actually the rare one? When you line Uranus up next to the exoplanet zoo, it stops looking like a mistake and starts looking like a data point. One sample from a huge distribution of possible worlds. In that picture, weird isn't a bug. It's the entire feature set. The universe is running a billion different experiments in gravity, chemistry, and angular momentum. And Uranus is just one of the more dramatic results. And yet, something is above the planets. Something is below them, not in space, but in our expectations. We put Earth on a pedestal and push worlds like Uranus into the basement labeled exceptions, so our mental solar system can stay flat and tidy. If we let Uranus into the definition of normal, the whole picture changes. It trains you to expect extremes, to be ready for planets with permanent day hemispheres, fractured magnetic seasons, oceans of supercritical weirdness. Because once you expand your sense of normal out to include a sideways ice giant, you're much more prepared for whatever waits in the next star's glare. And that's where this really matters. The more we look, the more the galaxy is going to try to surprise you. The question is, will you let it? So let's upgrade the picture in your head. Not the poster on the classroom wall, the one behind your eyes. Because here's what nobody tells you. If your inner solar system is still that flat, tidy diagram, Uranus will always feel like a mistake instead of a clue. Now let's begin. Close your eyes for a second and put one thing in the dark. The sun. Just a white gold sphere, hanging in black space. No labels, no grid. Around it, we're going to build a new solar system from scratch. First, lay down the orbits. Not perfect circles on a glass table, but glowing tracks that are slightly stretched, slightly tilted. Mercury's path a little off the main plane. Venus and Earth close to level. Mars just a bit higher or lower as it goes. You know the one your textbook showed you like beads on a wire? This is that, but in 3D with depth you can actually feel. Now drop in the planets themselves as illuminated marbles, each one spinning. Give Mercury almost no tilt, its axis barely leaning. Tip Earth by that modest 23 degrees you've heard about 1,000 times. Nudge Mars a little more rugged, then let Saturn bow gracefully, rings like a celestial hula hoop, tilted to match its spin. And then there's Uranus. Take that glowing cyan sphere and push its spin axis almost all the way over, about 98 degrees, so it's practically rolling around its orbit on its side. Its north pole doesn't politely point up from the orbital plane. It points somewhere weird, off to the side, like the planet lost an argument with gravity a few billion years ago. So, let's start at the very beginning of how that changes your mental model. Around each world, wrap a thin disk where the equator is, and let rings and moons live there. Around Saturn, that's easy. Rings wide and bright, moons skating along the same broad lane. Around Earth, you can picture the moon's path, almost but not quite in our equatorial plane. Now swing back to Uranus. Its equator is vertical compared to the ecliptic, so in your mind, rotate its ring system until those delicate bands stand almost upright, like a cosmic CD jammed on its edge. Its moons join in, looping in that same skewed plane. And yet something is above the planets. Something is below them. You've just changed which direction that is. Speed up time. Let the planets race around the sun, their tilted axes tracing cones in space. Watch seasons flicker on Earth in quick, familiar bursts. Then slow your gaze at Uranus. As it crawls along its 84-year orbit, imagine one pole staring straight at the sun for decades, drowning in unending day, while the opposite pole sits in a 42-year night that never sees a sunrise. This is your new solar system. Messy, tilted, dynamic, with no single correct up. Only reference planes we choose. In this version, Uranus isn't broken. It finally fits. The question is, once you can see it this way, what else stops looking wrong and starts looking dangerous instead? So now we can say it out loud. The flat poster in your head has officially broken, and in its place, we've been building something messier, stranger, and much more honest. You know the one. The textbook solar system where every planet stands upright like a polite spinning top, circling the sun in perfect rings, all sharing the same tidy plane, all enjoying neat one-year season cycles like Earth's. That picture shaped how we think about orbits, about up and down, about what a normal planet is supposed to look like. Because here's what nobody tells you. Even the simple part of the solar system was never truly flat. From the moment that collapsing cloud spun itself into a disk, gravity gave us a thin structure, not a two-dimensional one. Each orbit is tilted by a few degrees. The asteroids and Kuiper Belt objects are flung far above and below the ecliptic, and the Oort cloud wraps the whole thing in a vast spherical halo. That original classroom diagram is less a map and more a logo. Once you see that, Uranus stops being an embarrassing exception and starts being a headline example of how wild that three-dimensional theater can get. A 98-degree tilt sounds illegal in a flat diagram. In 3D space, it's just one more outcome of a violent past, probably a colossal ancient impact that knocked the planet onto its side and scrambled its interior. In a flat picture, it looks wrong. In a collision-scarred system, it's exactly the kind of orbit and spin we should expect somewhere. So what do its seasons really tell us? Not that nature broke the rules, but that our first rules were too simple. Uranus's 84-year orbit means each season lasts about 21 Earth years. Near solstice, one pole points almost straight at the sun, soaking in unending daylight, while the opposite pole is locked in a decades-long night. That bizarre pattern isn't magic. It falls straight out of geometry, tilt, and orbital period. Change the angle, change the year length, and you change the script for how sunlight sweeps across a world. And the weirdness doesn't stop at the surface. Its magnetic field is tilted by about 59 degrees from its spin axis and shifted off-center, so its magnetosphere lurches and pulses through the solar wind in ways Earth's never does. Its atmosphere looks quiet for years, then bursts into storms as the seasons change and sunlight finally creeps into long frozen latitudes. Different layers, same story. A planet reoriented by impacts, still negotiating the consequences. So hold on to this new core image. Not a flat disk of identical marbles, but a tilted theater of worlds, each with its own orbit, its own axis, its own lighting design for seasons. And yet, something is above the planets. Something is below them. The question now is, in a solar system this three-dimensional, what else is lurking off the neat, printed plane you grew up with? So when you zoom back from that tilted theater of worlds, one planet keeps heckling the show. Uranus is the one that stands up in the middle of the neat diagram and says, "Your rules? Those were cute." Because here's what nobody tells you. Before Voyager 2 flew past in 1986, we thought we had a decent mental picture of what a normal planet should be. Spin axis roughly aligned with the magnetic field. Interior layered in a tidy way. Seasons just a milder or harsher version of Earth's. Then Uranus rolled into frame, literally on its side, with a 98-degree tilt, and the data refused to behave. Voyager's instruments expected a magnetic field, more or less centered and lined up with the spin, like Earth's. Instead, they found a field tilted about 59 degrees from the rotation axis, and shoved off from the center by a third of the planet's radius. Imagine drawing a bar magnet, then realizing the real magnet is not just crooked, It's been kicked out of the middle of the planet entirely. The textbook picture broke on contact. And that's the point. Uranus forced astronomers to rewrite assumptions about how gravity, rotation, and magnetism are supposed to cooperate. Its sideways spin hinted at a colossal, ancient impact. Its ice giant interior doesn't match simple models of layered rock, liquid, and gas. Its magnetosphere flips from one bizarre configuration to another as it orbits, giving it magnetized seasons that don't line up with the light and dark seasons at all. What do you even call summer when your pole is in sunlight for decades, but your magnetic field is doing cartwheels? So, let's start at the very beginning of what this really means. We built our first rules of planetary behavior from a sample size of 1, Earth. Then a few more, the other inner planets, Jupiter, Saturn. From that tiny collection, we inferred what a typical orbit, tilt, and field should look like. Uranus is the reminder that the universe does not care about our tidy averages. Our models are provisional sketches, not the final map. You know the one. The comforting idea that nature prefers simple, symmetric, almost human-friendly designs. Uranus is the quiet voice in the back of the solar system saying, or not. And once you hear it, you start noticing echoes everywhere. Because every time we discover a hot Jupiter skimming its star, or a super Earth packed into an orbit shorter than a work week, or an entire exoplanet system tilted relative to its star's spin, we're replaying the Uranus lesson on a grander stage. The weird ones are not mistakes. They're the pressure points where reality pushes back on our assumptions. So when a planet's data makes you uncomfortable, that's not a bug in science. That's the moment just before the breakthrough. The universe is telling you the flat picture was never enough. Now let's begin to see what else it's hiding. So let's cash that in on something personal. If you had to live with one set of the seasons, would you pick the world you know? Or the one that's basically rolling through space on its side? On Earth, your whole life is braided into a tight one-year loop. Spring, summer, autumn, winter. You know the one. The sunlight swings back and forth by a few tens of degrees. The days stretch and shrink, and your calendar, your holidays, even your mood track that rhythm. You sleep because night shows up every 24 hours. You work because the sun reliably climbs, arcs, and sets. Because here's what nobody tells you. Your sense of normal is really just your nervous system syncing to a very specific orbital pattern. Now imagine you're on Uranus and we ask the same question. Do you still recognize what a season is? At the poles, the answer is almost no. One sunrise, 42 years of daylight. One sunset, 42 years of night. A single summer, there is longer than a human career. A full Uranian year is 84 Earth years, so a complete cycle is a lifetime project. If you were born at polar dawn, you could grow up, grow old, and never see true darkness until the very end. Move down to mid-latitudes and time itself feels stretched. The sun doesn't just rise and set each day. It slowly crawls around the sky as Uranus orbits, seasons unfolding in slow motion. Shadows migrate not over hours but over decades, and layered on top of that, the planet's lopsided magnetic field, tilted almost 59 degrees from the spin axis and shoved off-center, drags the auroras and radiation belts through their own bizarre magnetospheric seasons. Day versus night, summer versus winter, quiet versus charged space weather. None of those planes line up cleanly. So, which package are you choosing? Earth's quick-cut montage of change, where you get dozens of full seasonal cycles in a lifetime, or Uranus's epic generational arcs, where winter is coming is not a meme but a prophecy your grandchildren will finish living through. Do you want the comfort of a daily reset, or the strangeness of watching the sun's position in the sky become a family heirloom? And yet something is above the planets. Something is below them. On Earth, we use that flat mental picture to anchor identity. I'm from the north. I love autumn. I'm a night person. On Uranus, those labels would fracture. Are you a child of the long dawn? An artist of the endless noon? A scientist chasing a magnetic field that refuses to point the right way? So, let's start at the very beginning of that choice. Because once we ask which seasons you'd live under, we're really asking how far you're willing to let a broken orbit break your imagination. And Uranus hasn't even played its strangest card yet. So, let's start at the very beginning of that choice, by going back to the place we opened this whole journey. You're standing at the pole of Uranus. The sun is nailed to one point in the sky. It doesn't rise. It doesn't set. For 42 years straight, it just hangs there in a pale, distant glare. Then, one day it slips. The long dawn you were born into becomes a long dusk. The sun skims the horizon, fades, and then it's gone. Night doesn't last for a few hours, or a season on your calendar. It lasts for another 42 years, because here's what nobody tells you. This isn't a weird orbit problem. The orbit is almost boringly normal. The paradox we started with was simple. How can a planet that follows the same basic path around the sun as everyone else have seasons that look completely broken? The answer is that Uranus took the flat solar system rulebook and rotated it by 98 degrees. Its spin axis lies almost in the plane of its orbit, so the poles take turns pointing almost straight at the sun. The year stays the same, about 84 Earth years, but the way that light is shared out over that year is spectacularly wrong by Earth standards. And yet, something is above the planets. Something is below them. On Uranus, above, is the direction of that ancient impact that likely knocked the whole world onto its side. Below is buried in a deep, off-kilter interior that drags the magnetic field into another kind of misalignment. The field is tilted about 59 degrees from the spin, shoved off center by a third of the planet's radius. So its magnetic seasons roll and lurch just as dramatically as its sunlight. What you're really seeing here is that seasons are geometry. Change the angle between spin and orbit, and you rewrite the script for light, weather, and magnetism. Add a colossal collision in the early cloud of forming worlds, and you get a sideways ice giant whose storms flare near equinox, whose rings appear and vanish from our line of sight, and whose poles host decades of unbroken day and unbroken night. And yet, we built this whole picture from a single flyby. One spacecraft, one quick pass in 1986, catching Uranus near southern summer, when one pole stared almost directly at the sun. Everything else is inference, models, and a lot of patient guessing held together by gravity and physics. So imagine what happens when we go back. When a new mission watches an entire season turn, dives through that skewed magnetosphere, and sees how a sideways planet really breathes. Until then, Uranus can live in your mental sky as a quiet reminder that our solar system is not flat, not simple, and not finished. The diagrams you grew up with were just the first draft. The universe is stranger and richer than that picture ever hinted. If you've stayed with us from a sideways impact billions of years ago to an 84-year orbit compressed into a couple of hours, you're not just casually curious. You're the kind of person who lets their whole mental picture of the solar system get broken and rebuilt on a Tuesday night. Because here's what nobody tells you. Most people tap out long before a planet's seasons start lasting decades. So if this tour through Uranus's broken year rewired something in your head, don't just let it drift past like a lone cloud in deep space. Now let's begin a longer orbit together. Hit subscribe, turn on notifications, and you'll be there the next time we tilt another normal world on its side and see what falls out. We're going to keep chasing the places where the diagrams snap, where the neat flat plane stops working. You know the one. That tidy poster where all 8 planets circle politely, like beads on a wire. Uranus just tore a hole straight through that. Next up, we want to follow that thread into other broken worlds. What does Neptune's own warped magnetism look like when its magnetic field is tilted and off-center, twisting through the solar wind? What happens on a tidally locked exoplanet where one side bakes in permanent day while the other is frozen in endless night, and the only habitable zone is a thin ring of twilight around the terminator? And yet something is above the planets. Something is below them. The same way we climbed out of the flat diagram to see Uranus rolling along its orbit, we can climb again into the chaotic early solar system, when gravity flung worlds around like billiard balls, and normal had not been invented yet. Would you want to see that? To watch the collisions that could knock a planet onto its side, or fling icy bodies into the Oort cloud at the edge of interstellar space? Tell us in the comments what part of Uranus's seasons surprised you the most. Was it the 42 years of daylight at the pole, the decades of darkness, or that lopsided magnetic field precessing like a broken compass? What sideways question should we chase next? A world with no sunset, a planet with no stable seasons, or something even stranger you've been quietly wondering about? Because once you start to see how fragile our flat, tidy pictures really are, it's hard to go back. Subscribing isn't just clicking a button. It's joining an ongoing project to replace those classroom diagrams with deeper, more honest, three-dimensional stories. We're going to keep pulling on these tilted threads, from Uranus to Neptune to worlds we haven't even discovered yet. Stay with us, and let's see how far this broken orbit can really go. We've followed this broken orbit as far as it can take us. Now we have to zoom out and ask a bigger question. What does a sideways world really mean for the way we picture planets in the first place? Because here's what nobody tells you. Uranus's seasons aren't just weird trivia. They're a crack in the idea that there's such a thing as a normal planet at all. A world that rolls around the sun on its side, with poles that can sit in daylight or darkness for 42 years straight, is telling you that planetary formation is violent, messy, and three-dimensional. Giant impacts, migrating orbits, tilted planes of rotation. This is the rule, not the exception. So when we say Uranus's seasons are more broken than its orbit, that brokenness is a feature, not a bug. It's the scar that lets us read the past. That 98-degree tilt, it's a fossil record of some ancient catastrophe in the early solar system. The lopsided magnetic field, tilted and shoved off-center, is another clue that deep inside, the planet doesn't match the tidy diagrams. You know the one. The straight arrows, the clean axes, the polite centered dipole that never existed. And yet something is above the planets. Something is below them. Once you've seen Uranus ignore the proper way to spin, it gets harder to believe that our flat classroom orbit picture is the full story. Somewhere out there, around another star, there is almost certainly a planet. that makes Uranus look conservative. A world with a tilt past 120 degrees. Or a double planet locked in a gravitational dance where each hemisphere takes turns facing perpetual day for centuries. What kind of seasons does that give you? What does winter even mean on a world like that? Because the moment we started finding exoplanets, the universe began answering our questions with, think stranger. Hot Jupiters skimming their stars on orbits so tight they defy our old formation models. Super Earths with crushing gravity and oceans deeper than our entire atmosphere. We haven't yet seen a perfect Uranus twin out there, but the odds that it's the weirdest thing in the galaxy are very low. So here's the quiet homework the sideways ice giant leaves you with. Every time you see a flat solar system diagram with the planets marching neatly along one plane, remember there's a world out there casually spinning on its side, its poles taking turns, staring straight at the sun. Let that bother you, just a little. Let it poke at the edges of your mental picture. Now, let's begin a different kind of exploration. You can click into the next video, dive into more papers, or just step outside and look up. The sky above you looks calm, but it's built from collisions, tilts, and broken expectations as wild as Uranus's 40-year days. In a universe with no absolute up or down, no guaranteed normal, Uranus is our reminder that reality is under no obligation to match our diagrams. That's exactly what makes it worth chasing. So stay curious, keep questioning the flat picture, and we'll meet you in the next orbit.